Hey guys, I hope you're having a great day today. So today we are going to talk about interprocess communication, which is commonly called as IPC, and we're going to see how processes communicate with each other inside an operating system. So without any delay, let me quickly open the presentation that I have here. All right, first things first, what is a process? A process is basically any program that you have written which is being executed on your operating system, right? So today we are just going to see how two processes can communicate with each other. Okay. So for today, we are going to look at what an IPC is, what or why is interprocess communication required. Then we are going to go through various forms of IPCs which are present. So basically, if you have two processes, we are going to see how they can communicate with each other. So there are about 5 ways that I have come up with or I have come across. So we will go through each one of them with examples wherever possible. Okay, so the first thing, what is an IPC? Okay, so as you know, humans are social animals and communication is very important for us, right? Yeah, communication is the key for success. So to generalize, communication is important to get to know what other people want to tell you, as well as to communicate or to put across your thoughts as well. Right, so I'm not an expert with human communication. So in this video, we are just going to look at how processes communicate with each other in an operating system. So just to tell you guys that IPC stands for inter-process communication. We are going to use this jargon almost in the entire video, so I hope you remember that IPC stands for inter-process communication. Okay, so we are good with what is IPC. It is very easy to understand. So basically, processes want to synchronize with each other, they want to talk to each other and all of that, and that's the reason we want inter-process communication between them. Okay, so the first thing that we're going to look at is shared storage. Okay, so I am pretty sure that as soon as you think of two processes wanting to communicate with each other, the first thing that you would come up with is also something like a shared storage or some file where a process can write data to and another process can read data from and all of that. So again, the first thing that we are going to look at is shared files within shared storage, right? So basically, what is a file here? We are talking about a file which is present on the disk. Okay. So we have a small diagram. We have a producer and a consumer, right? So there is process A, which I've labeled as producer, and process B, which I've labeled as consumer. So let's say process A wants to send some data to process B. So how would it go about doing that? Is it will create a file, or let's assume a file is already present. Process A writes some data to the file and process B reads data from the file. That's how process A is able to talk to process B. They cannot directly go and talk like humans wherein I go tap on someone and I start talking. That is not possible with processes. So that's the reason we need some kind of intermediary in the middle to help them communicate. So have you come across race condition in this? So when you just look at this diagram, you do observe that process A is trying to write to a file and process B is going to read from the file, right? So let's see what happens when the producer and consumer access the file at the same time. Okay, so what I mean by that is, let's say process A is writing data to the file. Let's say it has to write 3 sentences which process B has to read. But as soon as process A finishes writing 2 sentences, process B starts reading the file. Okay, so this means that process B reads only 2 lines of the file and the third line is lost or it is not read by process B, right? So this is something which is commonly seen in this type of IPC. Okay, so yeah, the single biggest problem is the illusion that it has taken place, right? So now we introduce another concept called as file locks to overcome the race condition that I was talking about. Okay, so this might look complicated, but it is really easy. So basically, a file lock is a way to prevent a race condition from happening. Okay, so there are like I think 5 conditions here. So let's go through each of them. So there is a producer who has to gain an exclusive lock. Okay, so as we saw in the diagram, a producer writes to the file, right? So here we call this lock as an exclusive lock. Okay, we will come to what it means. Then there is a consumer which reads data from the file, and it has to gain something called as a shared lock before starting to read from the file, right? The next thing, if we notice, exclusive locks can be held by at most one process at a time. Okay, so basically this means that only one producer can be writing to the file at a time. We cannot have two or three producers writing to the same file at the same time, right? So this is one more condition which prevents producers from more than one producers from writing to the file at the same time. Now, one more thing that we come across here is to optimize reads. We should be allowing multiple processes or multiple consumers to be able to read from the file at the same time, right? So if a consumer is able to get a shared lock, or if multiple consumers are able to get a shared lock, they should be able to read the file at the same time. So this is what this line tells, this condition tells. Then we have the last condition wherein no process can write to a file if any process holds a shared lock on it. Okay, so what this means is there cannot be any producer, okay, which is trying to write to a file, but let's say someone is reading from the file. That is if someone holds a shared lock on the file. Okay, so this is not allowed because you have to wait for the read to complete, and once the shared locks are given up is when the writer can go and write into the file, right? The next thing that we see is writing to a disk is kind of slow, right? We can optimize this again. So since disk IO is kind of considered as a burden here, what we try to do next is we come up with another solution for an IPC wherein we use the shared memory. Okay, so we have memory allocated to each process. We allocate a small portion of it as shared memory, and then we allow the processes to write to the shared memory instead of writing to the file. Okay, and here by memory we mean RAM, which is random access memory. It is not your disk or anything else, and this is considered to be much faster than your hard disk or even SSDs for that matter. Okay, so RAM is much faster than your hard disk as well as SSDs. So the next concept that we introduce here is called semaphores. Okay, what is the use of semaphore for us right here is it is going to replace file lock. Okay, previously we had come across file locks, right? So these are again locks are something like small files on the system again, which are on the disk. So we are trying to optimize that by having something called as semaphores inside your memory. Okay, semaphores are nothing but just a normal variable which will hold a number inside it. It's an integer variable basically. Okay, and you can read more about file locks. I will put a link in the description and you can go read about how to create file locks and how to use them. So now let us look at how a generic semaphore works. Okay, a generic semaphore is also called as a counting semaphore, just for your information. So let's take a quick example here. So let's say you own a bike rental shop and you have 10 bikes in the shop which can be rented out. So basically, let's say you start with a semaphore value which is initialized to 0. If someone is coming to borrow a bike, what you do is you increment the semaphore value by 1. Okay. So as soon as someone borrows a bike, the semaphore value becomes 1. And if someone comes back and returns a bike, the semaphore value is decreased by 1. Okay. So let's assume 4 people rent a bike and 1 person returns it. The semaphore value is going to be incremented from 0 to 3, 0 to 1, 1 to 2, and 2 to 3, and 3 to 4 because we have 4 bikes which are rented out. And since 1 person is returning the bike, it becomes 3 from 4. Okay, I hope you understood this. It's just basically incrementing and decrementing the semaphore value. So what happens when the semaphore value reaches 9, right? So this is like the maximum number of bikes that can be rented out. Since there are 10 and we're starting from 0, you can reach a maximum value of 9, and only if someone returns a bike is when another person is allowed to borrow a bike. So every time you don't have to go and count the number of bikes. Instead, you just look at the semaphore value, and based on that, you take a decision if you want to rent a bike or if you have to wait for someone to return it. Okay. So basically, how do we use semaphores for us in place of file logs is we're going to use something called as a binary semaphore. Okay. So here the binary semaphore can have a value of either 0 or 1. It is also called as a mutex log sometimes, which stands for like mutually exclusive log. So it can either be 0 or 1 at once. So based on this, we allow operations to happen on the file, on the shared memory basically. Okay, so let's see how this works for us. So again, the semaphore value is initialized to 0. A process is allowed to write to the shared memory only when the semaphore value is 0. Okay, if the semaphore value is 1, we clearly know that only reads are possible or whatever, but writes are not allowed when the semaphore value is not 0. Okay, so the next point is after the write completes, the process which is written to the shared memory increases the semaphore value by 1. Okay, once the write completes, the semaphore value is increased by 1, and the process or the consumer that we came across previously can read from the shared memory whenever it wants, since the semaphore value is 1. Okay, the last point obviously is a process will be allowed to read only when the semaphore value is set to 1. Once the process finishes reading, it has to set it back to 0 so that writes can be performed on this shared memory. Now let us look at a drawback of using shared storage. This is applicable to shared memory as well as shared files. Okay, so this does not really work well with processes that want to exchange a stream of data. Okay, so this works well only when a process writes and then forgets, and some process comes and reads and then it allows to write again. This shared storage method does not allow you to read and write data streams, that is continuous flowing data. Okay, and for this we come up with various other solutions and other methods of IPCs. So next we move on to pipes, right? So what comes to your mind when you hear the word pipe? Oh, I hope it's not that one. This is what we are talking about. This is a normal cylindrical pipe. Okay, and what we understand is we again have a producer and consumer here in this example as well. So throughout IPC, whenever we talk about a producer, it is some process which is wanting to write, and a consumer is something that is going to receive the data which the producer sends. Okay, and both of these, the producer is on one end and the consumers are at the other end of the pipe. And it is like a common intuition that you can have. A producer produces data, it goes through the pipe and reaches the consumer. And here we talk about FIFO, which is first in first out. Okay, so the data which is produced by the producer, uh, so basically the first byte which is written by the producer is the first byte which is read by the consumer. I hope that makes sense. There are again different types of pipes here. The first one that we're going to explore is called unnamed pipes. Okay, and I have a small demo here. So it would be good if you guys are on your computers and if you can open up your terminals and do this along with me. All right, so we have pasted the command in the terminal. Okay, so we are going to sleep for 5 seconds and then we are going to echo hello world. Okay, so basically sleep means wait for 5 seconds in your terminal, and the next, so basically these are two processes which will run. First process is process A, which is going to just sleep for 5 minutes doing nothing, and the process B is going to print hello world on your screen. Okay, so if you see hello world is printed, and it is waiting for 5 seconds to exit the process 1 as well. Okay, so this is exited. Now if we look at this, it just tells that the writer is to the left, which is sleep 5 is basically the writer, and the echo command that we have here is the reader, which is to the right. So basically anything that this process writes can be read by this process on the right on this side. Okay, now here is a quick exercise. So you guys will have to find out, why does the hello world print before the writer completes. Okay, so if you notice here, we have hello world printed first, okay, and then the writer is allowed to complete, and then the process exits. The entire command that I have here exits. Okay, so you will have to find out why isn't this echo hello world waiting for 5 seconds, because the writer will have to finish writing and only then the reader is allowed to read, right? So why isn't the reader waiting for the writer to finish and then only printing hello world? So this is a quick exercise, and if you're able to figure this out, I would like you guys to put it in the comments, put the answer in the comments, and let's have communication in the comments. Okay, here is one more example that I wanted to show you. So we have a simple file called test.dat. Let me just move to temp folder. So I have the file here already. Okay, this is called test.dat, and this is the way the world ends. Okay, I've just split it into various lines and put it here. So I'm going to run this simple command. Okay, what it's going to do is basically it is going to print the contents of test.dat. It is going to sort it, and then it is going to print only the unique elements. Okay, so basically cat.dat is going to give an output. Sort is another process or another command which accepts an input, and sort basically processes it, sorts the words in alphabetical order and gives the output to unique. Okay, unique basis basically receives the output of sort, and then it prints only the unique elements in the entire file. Okay, so if you notice, the was repeated twice and it has been removed, and these words are printed in alphabetical order. Okay, so this is a very simple example. What we can also do is we can put a sleep 5 in between, right? So we can do this. Okay, and let's see what happens. Something really interesting is going to happen now, and the program returns without even printing this output, even though we had seen previously that sleep had to basically wait while the other processes could have executed, but in this case it did not really print this even before waiting or after waiting. Okay, so this is quite interesting. What we get to know from this is the pipe is unidirectional. Okay, so basically whatever cat program emits out as output is given to sleep 5 as input, and sleep 5 is not going to take any input. It is just going to wait for 5 seconds doing nothing. So basically the data which is sent is lost here. Okay, the buffer that it creates to send the output of test.dat to sleep 5 is lost, and it is not given to sort. And since an empty or a null character is given to sort, it doesn't do anything, and similarly unique doesn't do anything as well, and nothing is returned as output here. Okay, so basically we can have only one producer and one consumer in unnamed pipes, and you can obviously find some hacky solutions to overcome this, but it is not really recommended. So let us look at storage of data in unnamed pipes. So basically the operating system maintains an in-memory buffer for unnamed pipes. So every time you have a unnamed pipe in your command, there is there is basically a small part of the memory which is called as buffer, wherein all the data which is to be written and read from is present. Okay, so we do not really have concept of files in unnamed pipes. Okay, all of this is present in the memory itself, and the buffer is reclaimed once the reader and writer terminate. So once the entire data is written as output and the reader processes the data, the buffer is cleared or it is reclaimed back. The next thing that we talk about here is called named pipes. Okay, so how let's see how a named pipe works. Basically, let's look at that with an example, and then maybe I can quickly take you through what each of this stands for. Okay, so basically we have two terminals here. Okay, one on the left and one on the right. I'm making sure, I would really recommend you guys to try this as I'm doing it, so that you guys also get a first-hand experience of how named pipe works. Okay, so we have two terminals with the same working directory. The second thing that we will have to do is we will have to create a FIFO. Okay, let's assume the left side is the producer and the right side of my terminal is the consumer. This is going to write and this is going to read data. Okay, you can make a FIFO from any terminal. Okay, I'm just going to name it Aditya for now. Okay, so the type of the FIFO file which is created is P here. It is not a directory or a normal file. Okay, and what is going to happen now is we are going to start writing to it, right? Okay, and this is going to be the consumer which is going to read from the named pipe. Okay, so let's see the next process. You're going to input data. Okay, so basically cat and greater than Aditya means just allow me to put all my standard input into Aditya. So anything that I type now is going to get into Aditya and it is going to reflect on the right terminal, which is the consumer. Okay, so if you see on the left side, as soon as I keep typing anything, it is reflected on the right side, including special characters and whatever. Even the enter key is reflected on the right side. So this is a great way to actually sync processes when using named pipes. Okay, so let us quickly quit this. Okay, and if you notice Control C, when I put in the producer, it reflected on the consumer as well, and even it quit reading from the file. This is quite interesting. Okay, the next thing is you are supposed to unlink the FIFO that you created. Okay, that's it. So if I try ls of Aditya, it will not exist. You cannot do rm and force delete Aditya. You will have to unlink it so that all the processes which are reading and writing from it are also stopped from doing so. Okay, one more important thing to note here is we can have multiple producers and consumers for a named pipe, which was not possible in case of unnamed pipes. So that's all about pipes. Let us move to something called as message queues now. What are the disadvantages or what are the situations where we cannot really use a pipe? Okay, so if you notice, pipes have a really strict FIFO behavior. What I mean by that is every byte that I write as input, a consumer is going to consume it immediately. You do not have control as to what to consume and what not to consume. Okay, so you're basically going to consume all the messages that or all the bytes that a producer has written. Okay, let's say you have a requirement where you want only certain number of messages to be consumed, and what I mean by message is I will explain that in the diagram which is coming in the next slide. So basically a message is going to consist of two parts. One is the payload, which is actual text or the actual data that needs to be synced between the processes, and the other part of the message is the type of the message. Okay, this is basically represented by an integer. Just to clear out whatever confusion we had, so we have the same diagram again. We have a producer, we have a consumer, we have two processes A and B. The producer writes data, the consumer reads data, and here we have a message queue now. Okay, so let's assume the producer has written the messages 1, 2, 3 and 3. Okay, I'm going to represent only the message types here. The data is kind of hidden right now, and but you can assume any junk data behind each of these numbers. Okay, so basically what this means is there are three types of messages in the message queue. The types are defined by the numbers. So whatever is one type of message, two represents another, and three, these two messages are of one type of the message. Okay, and the consumer is allowed to consume messages in any order. So basically if the consumer wants, it can start consuming 3 first and then 2 and then 3 again and then 1. Okay, so there need not be any specific order in which it consumes. It basically depends on how your program wants to consume data which is sent by the other process. So basically, if you notice, it is mostly meant for unidirectional use, right? So basically, a producer writes data and a consumer keeps on consuming. It is not a bidirectional. By that, what I mean is process B cannot start writing to the message queue. It is only one writer at a time and multiple readers or whatever at a time. Basically the data flows in one direction and not the other direction as well. Okay, bidirectional named pipes do exist, but it doesn't make a lot of sense to use them because by default they come with they are recommended to be used as unidirectional pipes. Let us look at how we can overcome this problem. Okay, so now this is the most interesting concept here, uh, which we use something called as sockets for interprocess communication. I think you must have heard of sockets already. So we are going to talk about two primary variants of sockets. Okay, these are one of it is called IPC socket. So basically, it is on the same host. Whenever you want to communicate, whenever you want two processes to communicate on the same host, you use IPC sockets. They are also called Unix sockets. And the other part is when you want two systems, the processes on two different operating systems or two different physical hosts to communicate with each other, you use network sockets. Now, this is a statement that I want to make here, which I will talk about later. So basically, sockets which are configured as streams are bidirectional by default. Okay, so only stream sockets are what are something that can have bidirectional transfer of data. And do you have any good example for IPC over sockets? Yes, you do use this every day. So whenever you visit a website, basically a client and a server talk over network sockets. Okay, so as a client, you have a socket locally on your system, and a web server will have a socket on its system, and the communication happens over sockets. Okay, so we talk about two major network sockets. We remember we are only talking about network socket here. The first type is called a stream socket, and the second is called a datagram socket. A stream socket is used for your TCP data. It is for transmitting data over TCP, and datagram sockets are used for transferring data over UDP. Now here is the question for you. Why only stream network sockets are bidirectional? So if you notice, stream sockets are for TCP and datagram sockets are for UDP. Now you will have to figure out why only stream sockets are bidirectional and not datagram sockets. Dgram sockets are only unidirectional. So here is the answer. So basically TCP has something called as three-way handshake, and it is a client server protocol wherein a client is going to establish a connection with a server. It is going to be a bidirectional communication wherein the client sends some data to the server and server responds back with the data with some data and all of that. So that's the reason you need both directions of communication over the same socket. But if you look at UDP, what happens is as a client or as a process, you just send data and you forget about it. You do not wait for an acknowledgement or for a response for your data. That's the reason datagram sockets are unidirectional and only stream sockets are bidirectional. If you really want to know more about TCP three-way handshake, I would recommend you to go and visit this link here. You can check this video which I've made previously, which explains TCP three-way handshake and a lot of other concepts as well. Now here is the second question for you guys. Uh, let's say you have a network socket which is present. How do you go about using it as a Unix socket? Okay, Unix socket is on the same system between two processes, and network socket is between two systems and again different processes. Okay, so how would you convert a network socket to be used as a Unix socket? You can again put your answers in the comment section and we can go through them. Now comes the last part, the last type of interprocess communications that you can have. So this is using signals. So basically you must have heard about interrupts, right? You must have heard about hardware interrupt, software interrupt. So let's say I press a key on the keyboard, it triggers a hardware interrupt. Okay, similarly, if let's say a process wants to talk to another process, or let's say I have a bash terminal running and I press Control C when a process is being executed, it is going to send an interrupt signal to the process. Okay, so basically signals can be handled, and that's how we are going to make use of it as an IPC. Now here there are two things which cannot be really handled. One is sig stop and one is sig kill. Sig stop is basically going to pause your process which is executing, which is being executed. And sig kill is basically when you issue a kill command to the process. So basically the process is going to get terminated by the kernel no matter what you do. Okay. However, there are other types of signals. Like for example, you can look at sig term. Okay, what happens in sig term is basically you're going to execute a process, and when you press Control C, the process has control over how to exit. Okay, so the process can do a few things like cleaning up and gracefully exiting instead of just returning back the control to you. Okay, so this is how you must have noticed sometimes that there is some program which is stuck and you keep pressing Control C and it doesn't return. So basically they wantedly do not gracefully exit as soon as you press Control C. They do a lot of cleanup, and you will have to wait for the process to give back control to you. So that is all I had for the video. Now that we have done with different forms of interprocess communications, here is a quick assignment for you. We have discussed about 5 types, so I would like you to quickly write 2 programs, 2 simple C programs or Python programs or whatever you like, and then you try implementing each of these interprocess communications inside your code. Okay, this is going to be quite interesting. If you're able to do this, it would be a great job and a great learning curve for you as well. Also, I'm going to link the entire presentation in the description of this video, so you can go and check out if you want like text or the video link or whatever. I would recommend you to go to the link and check out the presentation. Do like and share the video if you really like it and if you learned something from the video. And I highly recommend you to subscribe to the channel if you want more such videos, and if you want to be notified of these videos, click on the bell icon. Thanks for watching. See you all in the next video.